All right, 4.5 is the fundamental theorem of calculus. And any time in mathematics that somebody puts the word fundamental in there, it means this is really important, right? Doesn't always mean it's fundamental in the sense that it's really basic, although it might be, or at least basic for that particular topic. But it means it's very, very important for the topic, right? Now, there are two parts to the fundamental theorem of calculus that we're going to take a look at. These two parts, one of the other of them I'm going to put on your test, maybe both. So these are the ones where on this test you get to memorize something again, like on test 1 and 2, right? Didn't have anything on test 3 like that, but you get to on test 1 and 2. And so now on test 4. Fundamental theorem of calculus says that if you have a function that's continuous on AB, and its antiderivative is capital F, right? We looked at this notation back in section 1. Then if you want to find, this is actually a calculation for how to find it without rectangles. Good news, right? If you want to find the definite integral from A to B of a function, you can take the antiderivative, which you guys have been practicing on for your basic skills quiz, right? And you can evaluate it at the higher value, the value that's on top, the upper limit. And then you can subtract evaluating it at the lower value. And that's it. It's the calculus stuff from 4.1 combined with a little bit of evaluation algebra. That's it. And that finds for you the exact value instead of an approximation using rectangles. You want to see how easy it is? Let's do one. We have an integral from 2 to 5 of negative 3x plus 4. So what we're going to do is we're going to evaluate the antiderivative first. So this is a basic skills type question. What is the antiderivative of negative 3x plus 4?
Negative 3x squared plus 4.
And now when you do it on your basic skills test, you do the plus c, right? I want to show you what happens here with the plus c's to show you that we don't actually need it when we're doing definite integrals, and you'll see why in a moment. Let's put the plus c for a moment here, and then I'm going to show you why we don't need it, okay? So on an indefinite integral, the ones you've been working on, right, the ones for your skills quiz, the ones without the numbers on the top and bottom, you have to have the plus c. We've talked about why. It has this shift thing going on, right? When you're working with definite integrals, you don't end up needing it. Here's why. What we're going to do then, according to this theorem over here, is we're going to, all right, the theorem above on your paper, is we're going to evaluate this function at the larger value, which is the top value. It's not always a larger one, but the one that's on top, minus the value that's on bottom. Okay, so we want to evaluate the top value minus the bottom value. Now, in terms of looking at this, the way that we write that, sort of the convention that mathematicians have used, is to write this sort of vertical bar on the left and put the 5 on the top and the 2 on the bottom. It's not the script S, but it's just an evaluation bar. It says I'm going to evaluate at the top value minus the bottom value. So I'm going to have you write this out. You don't actually have to do the calculation out by hand, but I do want you to write it out so that I understand and you understand both of what you're actually doing with this. All right, so this is evaluating this at the value 5. And let's put this in a big bracket here for a moment. And then
Why are we leaving the plus c if we don't need it?
I'm going to show you why I don't need it yet. We haven't actually said why we don't need it. I'm telling you we don't, but I'm about to show you why. Yeah. So that's all of that evaluated with the value 5 in there, right? And then we're going to do the same thing with the value 2 in here. So obviously these first two pieces inside the bracket, those are just numbers. Your calculator is going to give us a number for that really just fine. Here's a second here. This is a plus c. That's just plus c, right? This is a number and this is a number and this is also a plus c. But notice this plus c has a negative in front of it. So this plus c and then minus this plus c means that the c's add to 0. Right? We've got a positive c, we've got a negative c there. And that's why we don't need the c's, is because they cancel each other out when we do the addition, or in this case the subtraction, I should say it that way, of the problem. So, and because of that, we actually don't ever really need to write the plus c in the problem because it's just going to add to 0 anyway. Okay? That's something a little different on this one. All right, these evaluations your calculator can do just fine. In fact, there's a couple of ways your calculator could do this. But let me have you actually, well, I've showed you one of them last time. Let me have you go ahead and evaluate it just by your calculator by plugging it in. So you can put this equation that you got for the antiderivative in y1, right? So negative 3x squared over 2 plus 4x. And then you can go into your table and evaluate at the number 5, go into your table, evaluate at the number 2. And then if somebody will give me those two values, I don't know if I have them written down separately. I don't. And then, or give me the value you get when you subtract them, then we'll have those values. What did you get when you plugged in the number 5? Mandy, you have 11 something?
17.5.
17.5. Negative? Okay. And then what do we get when we plug in the number 2? Negative 2?
No.
Positive 2. Okay. All right, so negative 17.5 and then minus the number 2. What does that give me? Negative 19.5. Now, we learned something last time that your calculator can do for you to make sure that you have the right answer, didn't we? So I want you to do it. I want you to check. You can either do it in the graph or you can do it in that main screen, either way, and use that Math 9 feature. So those of you, a couple of you weren't here last time, I know, but if you'll hit Math 9, actually you need to put the original equation in y1 first. The original minus 3x plus 4 goes in y1. We haven't done that yet. We still have our actual antiderivative there. So take your y1 and write in there negative 3x plus 4. Out on your regular screen, hit Math and select option number 9. All right. If it says FNINT, you have to give it some notation. Let me remind you that notation from last time. You have to tell it the function, which is y1. You get y1 underneath vars. Select y vars. Choose function. And then in y1. You do a comma, x, comma the lower limit, which is 2, comma your upper limit, which is 5. And if we've done it correctly, if we didn't make any mistakes, it should be giving us negative 19.5 as well. I've got some nods that this works. Yeah? So we get negative 19.5. So we can check all of our answers in this section. That's great, right? Yeah, it is. It's very nice. So this one ends up being negative 19.5. Let's try another one with some trig. Some of you are really struggling to remember where the negatives go with trig. So we've got the integral from 0 to pi of 1 plus sine x. So let's do it one piece at a time. What's the integral of 1? X. What's the integral of sine x? It is negative cosine x. Those negatives are getting lots of people in my office, so make sure when you come in to do your basic skills quiz, you know when and when you don't to put a negative, all right? We're evaluating this at pi and at 0. So this is actually one where you can do it in your calculator. I actually think it's probably quicker if you do it by hand. So this is pi minus the cosine of pi. And again, remember, we don't need the plus c's. We talked about in the last one. Minus 0 minus the cosine of 0. Well, pi is pi. That's all great. What is the cosine of pi? It's actually negative 1, right? So I actually have pi minus negative 1. Minus. The 0 is 0, so that's fine. There's a negative here, and then what's the cosine of 0? That is actually 1. So we've got a negative 1 there, but the negative is not coming from the cosine 0. It's coming from the subtraction sign that's already there. So I actually end up here with pi plus 1 plus 1, which gives me pi plus 2. And you do have to be careful because if you had plugged in pi in your calculator, it's not going to say pi, right? It's going to tell you something that you're going to have to then recognize that this is pi. And if you do it all in one fell swoop, you're going to be in a little bit of trouble because I suspect while you could recognize your calculator telling you pi, you probably aren't going to recognize pi plus 2 when it tells you that, right? But you can still confirm the answer with your calculator doing what we did on the board here above, right? So find out an approximation. What is pi plus 2 in your calculator? It's 5.14, right? And then some numbers after that. And you could do this function integration again. Again, you have to do the function integration with the original function, 1 plus sine x. You always do it with the original function. So if you type in there on your y1, 1 plus sine x, and you have it do function integration from 0 to pi, it should tell you 5.14 with further decimals. Did it work out? Excellent. All right, here's part 2 of the fundamental theorem of calculus. How does this look different than the one before? What do you notice that's different? Maybe let's start with this piece of it, right over here. What do you notice that's different about this integral? There's an x in the limit, right? There's actually an x in one of these limits, whereas before it's always been defined with a number at the top and number at the bottom, right? And x is not a number, it's actually a variable. It's a number that's changing, or at least has the potential to change. We don't know what the value is. This one says if f is continuous on AB, and you have the antiderivative, and it's equal to the integral from a to x of f of t dt, then if you were to take the derivative of what's on the left, you would simply get the function that you have on the right with x in the place of the t. So that sounds really very straightforward. And so let me kind of just give you an example here of something that would be very clean, so that then I can show you some of what happens when they're not so clean. So if this said the integral from 5 to x of t squared plus 7 dt, then what this is saying is that if you wanted to find the derivative, all you need to do is you need to rewrite the right-hand side with an x in the place. That's what this says. Does that make sense? Are you seeing those pieces? So taking a look at the next problem, what is different in example number 3 than this example that I just sort of made up? It has sine x up there, not just x. So something different is, in fact, going to happen. Now, part of it's going to look very much the same. So let's take a look at the part that's going to look the same. So we're going to find a derivative. The portion that's going to look the same is it really is going to look like the t gets replaced by sine x. The part that's different is this left-hand side said that I'm supposed to be finding a derivative, right? And I did. I found the outside function of a derivative. But the inside of this is sine x. This is a chain rule. This piece is the outside derivative. I need the derivative of the inside, and my inside function is sine x. What's the derivative of sine of x? Cosine of x. You have a chain rule in the middle of the problem. So when you're finding this derivative, the outside function was how we were defining everything to be happening over here in this fundamental theorem of calculus. But we have an inside function now that we also have to find the derivative of. So the last thing that we would do then is we would simplify this by writing this out. Sine x times cosine x plus 2 cosine x. Does that make sense? So if you ever, in any of the pieces, and actually we're going to see an example here in a second, but it doesn't necessarily have to be just the value on the top changes to not being x, right? But if any of the pieces actually don't have x as that, you've actually got a chain rule going on. All right, what's different on this one? The top and the bottom are variables, aren't they? Now that's a little weird because, in fact, this theorem over here, that a at the bottom, it really needs to be a number at the bottom for this theorem to hold true, just like it really needs to be an x at the top. So if we don't have those features, we've got to do something a little different to make it work. So let me show you what we have to do. The first thing we need to do is we need to get a constant number involved, and it really doesn't matter what the number is, so we're just going to use 0 as a default. But what we're going to do is we're going to take a theorem that we described it in the last section. We never really used it. Do you remember that theorem that said that if you have a point between a and b, you can break the integral into two integrals? Some of you didn't like it because the letters weren't in order. I had an a here and I had a b here, and then all of a sudden c was between them. I remember Taylor sort of saying, oh, I don't like that's not alphabetical, right? We're going to do that. So what we're going to see happen is we're going to go from x to 0 of our function t squared plus 4 dt. And then we're going to go from 0 to 3 minus x of t squared plus 4 dt. All we're doing is we're breaking it apart at the value 0 between the two. Okay, is everybody good on that step? All I've done is break it apart into two different integrals, and I'm allowed to do that. I saw we did a theorem in the last section, in section 4.4, that had that feature. Now, there's two issues here. There's issue with each one of these. The issue with this piece on the left is what? The x is on the bottom instead of on the top. You guys see that? Right. So we've got to talk about how we're going to deal with that. This piece actually looks like the last example we did, where it had the sine x on top. So we're going to have a chain rule on this one, where there's an inside function. But we already know how to deal with that one because we've already dealt with one like it. Okay? So let me talk to you about how we deal with this. I don't remember if I just skipped it. I don't remember seeing it in your book, but I didn't go back to actually look for it after when I realized that we hadn't talked about it. But you can change the limits of integration's location. That is, you can flip the upper and the lower ones into different order if you put a negative in front. So there's a theorem that says if I have the integral from a to b of f of x dx, that's an x, then I can rewrite this as b to a of f of x dx by simply making it negative in front. So I'm allowed to switch the limits of integration, just switch the upper and the lower limits, if I put a negative in front of the function. Okay. So up here, then, I'm allowed to take this and put a negative integral from 0 to x of t squared plus 4 dt. And then I also have this integral from 0 to 3 minus x of t squared plus 4 dt. Okay, so that's a property of integrals. The beautiful thing is that except for the negative, this first piece looks exactly like the fundamental theorem of calculus part 2. Doesn't it? Got an integral, starts at 0. 0 is the a value, goes up to an x of the t squared plus 4, which means for this piece, all I have to do is to replace the t with x. And it's got the negative in front still. So I am going to distribute that negative here at some point. Okay, so good? Ben, please. Okay, second piece. Well, the second piece is like the sine x one that we had on the previous example, right? We're going to take what that upper limit is and we're going to plug it into the t value. So that's the first step. So this is going to have 3 minus x squared plus 4. That's the outside derivative. That's how we were told to use that. And then we have to multiply that by the derivative of that upper value here itself. So what's the derivative of 3 minus x? Negative 1. Now, the difficult thing, at least, it's not difficult, it's just that it makes you stop and think, is that I just asked you to do a derivative in the middle of doing antiderivatives, right? Okay, and I'm going to ask you to do it again on Tuesday with a different type of a reason for that. But recognize that this is a derivative that we just did, not an antiderivative. The notations start to get mixed up if you're not careful. This is just algebra though, right? We're just going to simplify the algebra here. So I have negative x squared minus 4 plus, and I need to distribute this. This is a foiling type problem. So this is 9 minus 6x plus x squared plus 4 times negative 1. You can either distribute the negative 1 and then combine terms, or combine the terms and then distribute. Doesn't really matter. You're going to get negative x squared minus 4 on the left, or on the first, for the first piece. And then I'm going to have minus 9 plus 6x minus x squared minus 4. Collecting like terms, what do I have? Negative 2x squared plus a 6x, and I have 17 minus 17. Any questions? There's a lot going on in that one. I wanted to do one that was kind of complicated so you could see a lot of the pieces and how they played together.
Where did the negative one come from on the outside?
The negative one outside over here, it came from the derivative of the piece in red.
Oh, okay.
So when I plug this in, it does plug in just like the other sort of description told me, but that's the outside derivative. And then the inside derivative has to be the derivative of what's inside. That pays the red. Yeah. Okay, any other questions on this one? All right. I wanted to do one where you saw it sort of written in a different way. It's not actually asking you to do anything that's terribly complicated. But instead of actually giving you the notation, it gives you a description, which means you actually have to look at the graph to figure out what the notation should look like and then process it from there. So this one tells you we're going to find the area. That means find the definite integral of the region that is bounded by y equal x squared, x equals 2, and the x-axis. So you need to start out with your graph and a graph of x squared. Now this is one that you know what the graph looks like, so you may not even care to draw it if you don't want to. But this is a graph of a parabola, right? So you've got a parabola, something like this. And that's not too bad. And it's supposed to go out to x equals to 2. So here's x equals 2, and it actually says the line x equal to 2. So, I mean, that's like a vertical line. In fact, let me draw it in a different color just so that we don't think that it's a... Yeah, so this is my line x equal to 2. And it says the x-axis. Well, the x-axis is down here, right? So if you look at these three curves and where they cross each other, you see a piece of trapped area, right? The area that they're referencing is right in here. So what will that look like in integral notation? Take a second to write that down. What should that look like with this new definite integral notation that we introduced in 4.4 and that we've now been using in 4.5? Right, the script S and all of those details. What does that look like? Okay, so it starts at 0, because we start on the left and we go to the right, 0 to 2. Nope, it's not even that complicated. It's just x squared. See, this area is actually, the area description is always whatever curve is on top down to the x-axis. Our curve that's on top is actually x squared. And then I'm already being bounded below by the x-axis. They gave me that in my description. So this really just is the integral from 0 to 2 of x squared dx. Okay? That's easy to calculate. You guys know how to do that. What is the integral of x squared? What is the antiderivative of x squared? X to the third over 3. Evaluated from 2 to 0. And if we evaluate this at 2, we get... 8/3. If we evaluate it at 0, we get 0. So this is 8/3. So there's nothing necessarily complicated about the equation once you got it set up. I wanted you to have the experience of thinking about how you set one up based on the picture. Okay? All good? All right, one other thing in this section is an average value formula. So if we want to find the average value for an integral, that is sort of the image that you should have in your mind, is if you had one of these curves. Let me just use the x squared curve that we just had. If you had one of these curves from 0 to 2, and at 2, this one would have been 4, right? It was the line y equal x squared. And we found out that the integral itself had a value of 8/3, right? Well, what this formula is saying is that I could take that 8/3 and I could divide it by the length of the interval. That's what b minus a is. It's just the length of this interval. This interval length is 2. So I would get 1/2, the integral from 0 to 2 of x squared dx. We calculated this on the previous screen to be 8/3 times my 1/2. So this would actually give me 4/3, right? 1 1/3. This is actually telling me that if I had the number 1 1/3, so here's 2, 1, 3, 1 1/3 would be about right here. And imagine that this curve now, and I know it's area, but imagine just the picture being a volume kind of a shape, because it's going to be easier for me to manipulate. Or like a Play-Doh or something like that, a very flat Play-Doh. If you're to take the Play-Doh piece that is actually filling in this shape and you were to remold it into a rectangle, the area in this red rectangle right here would be the exact same area that was under the curve. So if you were to take this piece and be able to mush it down, it would actually fill this in to make it a rectangle. That's what an average value is. I mean, this is what happens with your grades, right? Your average grade does that, doesn't it? Takes all your grades and somehow sort of melds them down into what sort of it's sort of speculating you did sort of on average all semester. Okay, this is a visual imagery of that same idea. So the only difference in finding the average value is this extra piece at the beginning where you're really just dividing by the length of the interval. Okay, the length of, or the difference between your x values. And it writes it as a fraction of 1 over that instead of actually as division. Some textbooks will write it as division, but it's the same idea. Okay, that's the only difference. So we're going to take a function. Our function is the function square root of x. Our interval goes from 4 to 9. And I'm wanting to find the average value. So my average value will be 1 over 9 minus 4, the length of the interval. And the length of this interval is 5, right. Okay, so we'll have that in a moment. It'll be 1/5 in front. The integral will go from, the interval, goes from 4 to 9. So the integral will go from 4 to 9. And while I can write x as the square root of x, I can also write it as x to the 1/2, which is a little bit more helpful. So this is 1/5 in front. What is the antiderivative of x to the 1/2? Yeah, so I'm going to write it a little bit differently just for the moment. So this is x to the 3/2 over 3/2. I'm supposed to be evaluating this at 9 and at 4. And it is helpful, just like Ben said, to think about this as 2/3 instead of division of 3/2. The other thing that's helpful to think about this in terms of is what this x to the 3/2 really looks like back in that square root notation. So this is actually the square root, that's what this 2 here is doing, of x cubed. And the reason that's nice is because 9 and 4 are both easy to take square roots of. That's really why we want to do it. So I've got this 1/5 and this 2, I'm sorry, let me write that 9 and 4 in here. I've got the 1/5 and the 2/3. So that's actually 2/15, right? And we're going to evaluate that with the 9 in the place of the square root. So this is the square root of 9 cubed. And then we're going to subtract, evaluating that with the square root of 4 cubed. It doesn't make any difference, actually. I'm going to put it on the outside because it's easier for me to take a square root of 9 and then cube that value than to cube the 9 and then take the square root because the numbers are smaller. Yeah. And you might notice something I did here. I didn't really make an issue about it doing it, but I kind of left the multiplication factor out here in front and did the subtraction inside because the multiplication applies to both terms, and I just assumed multiply 1 time at the end as to 2 times in the middle. Make sense? So that multiplication factor I wrote in the front. So square root of 9 is 3, and then 3 cubed is 27, yes. So I've got 2 over 15. I have 27. Let's do the same thing with 4. The square root of 4 is 2. 2 cubed is 8. So what is 27 minus 8? 19. What is 19 times 2 over 15? 39 over 15. Which I think reduces because they're both divisible by 3, actually, right? 38. I was like, there's something wrong about that. I didn't think I reduced anything in my notes. There we go. 38 out of 15. And those don't reduce because neither is divisible by, the 38 is not divisible by 3 or 5. So we have 38 over 15. If you end up with an answer at the end that's actually a terminating decimal and you want to write it as a decimal instead of a fraction, that's fine. But I don't want to see any repeating bars. That's just bad math notation. We use it all the time, I know, especially with non-math people. Like my elementary education majors, I love them to death. They love repeating things, but we don't do that with real math. So we don't want to write the repeatings. We want to write them in decimal or in fractional notation. Okay. All right. Any questions on that? All right.